Yes.
Yep.
All right, so I guess we can start. So good morning, everyone. So welcome to the third part of our MoCaO lectures. And today we have a different speaker. So Dr. Chan Yan. So she will be presenting a slightly bit different topic, okay, still related to Tim's presentation on Monday and Tuesday. So Chan, so you can start.
Okay, thanks, Nadia.
Thanks.
All right, hello, everyone. So today, we're gonna talk about GMRS. Okay, so this is the outline of today's lecture. So at the beginning, we'll introduce what is GMRS, what it can be used for, and then we will derive GMRS, and we will see a few examples, and we'll do some convergence analysis. And at the end, if we have time, I would also like to talk about restarted GMRS. That's a different aspect to implement the standard GMRS. Okay, so now let's make a start. All right, so in the last two lectures, we have looked at projection method for the eigenvalue problem, where our main tool was the Arnoldi decomposition, okay, which is a Krylov subspace projection method. And now we're thinking about, okay, can we use this Krylov subspace, this Arnoldi decomposition to solve our linear system? Okay, so before that, we know that Arnoldi method is quite good at capturing the eigenvalue problems. Okay, now let's see if we can also use this to solve AX equals to B. And the GMRS, it stands for generalized minimum residuals. Okay, so GMRS. Okay, let's see. So to solve AX equals to B, once again, we build the Krylov subspace, okay, which is a span of these vectors B, AB, A squared B, all the way to A to the power M minus 1B. And of course, for our problem now, our vector B is not arbitrary. Okay, it will be from the problem that you're trying to solve. It's the right-hand side of the linear system. And our approximate solution XM, which we will choose, okay, which we will choose somehow from this Krylov subspace, okay, and this approximate solution will be a linear combination of these vectors B, A, B, okay. So that means that we can write our approximate solution like this, XM, the M's iteration is C0 times B plus C1 AB for some coefficients Ci. Okay, so or in other words, we can write this approximate solution as this is the polynomial of A of degree M minus 1 times B. Okay. And now, according to our Arnoldi decomposition from last lecture, okay, so now after the Arnoldi decomposition, you will get two matrices. One is the VM, and the other one is H bar M. And the VM has all the columns of VM form the orthonormal basis of the Krylov subspace, and the HM is has M plus 1 rows and M columns. Okay? We have these two matrices after the decomposition. So now our solution can be written in this way. So VM times YM. VM is has all the column, all the vectors also normal to each other, and then YM is some coordinate vector. So now the question is, all right, okay, so I know VM. So how about the YM? How do I figure out YM? Okay, right, that's our, that's one of the questions we're gonna figure out. For now, the next question we're trying to answer is that, okay, so we said that okay, my solution. Actually, how do I know that a good approximation could be found in this Krylov subspace Km? Why do we think that this is a good idea? Okay, that's the first question to answer. And if we know this is a good idea, then yep, that's very easy. So my xm next step would be just Vm times Ym. Okay, so let's focus on this question here. So according to the Cayley-Hamilton theorem, so if Pn is the characteristic polynomial of A, then the matrix A satisfies its own characteristic polynomial. So Pn A equals to 0. So that means we have so A0, A0 times I plus A1 times A plus A2 times A squared, means we have this this polynomial equals to 0. And note here that An is 1. Okay, the leading coefficient is 1. And then from here, let's multiply A inverse on both sides of this equation. So the first term would become A0 times A inverse. Second term becomes A1. A1 times I. So A times A inverse, that's I. And then next term, A2 times A. Okay, cancel out one of the A here. Okay, and then the last term here, it becomes An minus 1 equals to 0. Okay. And then the next line here, I did is just keep A inverse on the left-hand side and move the rest to the right-hand side, and then divide by A0. So the whole thing scaled by A0. Now let's have a look at this bit. Okay, so this is again, you can see that this is a polynomial of degree n minus 1. Okay, polynomial of A of degree n minus 1. So I know my A inverse can be written as a polynomial of degree n minus 1. Okay, so this is great. So we know that our exact solution x is A inverse B, and my A inverse can be written as a polynomial. Can be written as a polynomial n minus 1. And clearly we know that this Pn A B, this is definitely in the Krylov subspace of size n. Okay. So if you span the Krylov subspace all the way to size n, then this exact solution definitely in this Krylov subspace. Okay, so now here, the next line is all we asking here for our approximate solution is that we hope that our numerical method just choose a polynomial of a smaller degree, okay, m minus 1. Okay, remember that m is always less than n, or we hope that m is much smaller than n. Okay, we choose a polynomial of a smaller degree that this part doing a great job at representing this part. Okay, representing the action of this Pn AB. Okay, that's all we are asking. And so this is promising. This is definitely it's in this smaller Krylov subspace. So Km. And so this means this is in this smaller Krylov subspace Km AB. And if it's this vector in this Krylov subspace, then we know that it can be written as Vm times Ym. Okay. So that's why that's why we think that our approximate solution should be in this Krylov subspace, this Km. So now the next question we're trying to figure out is that, okay, now I know where to look for my solution. Then how do I figure out my Ym? Okay. So that's our next slide here. Okay, so just remind everyone that this is what GMRes does. It's trying to minimize the residual norm. Okay, our residual norm is simply the norm of B minus AXM. Okay, and use Arnoldi decomposition. Let me just write this down. Our Arnoldi decomposition, remember we have then showing up. Oh, that's better. Yeah. Our Arnoldi decomposition is A VM plus 1 HM bar. Okay, that's the two matrices we get from Arnoldi decomposition. So now let's have a look our residual. So Rm is B minus AXM, and XM can be, because it's in the Krylov subspace Km, so XM can be written as VM times Ym. Okay. And then here we're going to use the Arnoldi decomposition, AVM, replace AVM with this VM plus 1 times HM bar. So that's become this term here. Okay. And now so once we have here, let's have another look of B. Okay, what is B? Remember that the first column of VM plus 1 is V1. Okay, V1 is just a B vector normalized. So B divided by its norm. So normalize the B vector. That's B, V1. Okay, so that means B is V1 times beta, or beta times V1. Okay, so that's why we have this beta times V1 here. And then copy the second term down here. So now we can write, okay, another thing is V1, remember, is just the first column of this matrix Vm plus 1. Okay, so this Vm plus 1 times E1, that's really just giving you the first column of this matrix. So it's beta times this part, and then the second term remains the same. Now we can take this Vm plus 1 matrix outside. So leave us inside is just beta E1 minus HM bar times Ym. And now we're going to take norm on both sides of this equation. So this is the residual norm. And then right-hand side is taking the norm of this whole thing. And then here, note that Vm plus 1 transpose, Vm times Vm plus 1 is the identity matrix. Okay, because of the columns of Vm plus 1, remember they are also normal. So they see, okay, so Vm transpose times Vm is 1, is I. Okay. So that means our norm is simply just the norm of this beta times E1 minus HM bar Ym. Okay. Okay, so far so good. So now for our GMRes, you see that we're trying to minimize this left-hand side, this residual norm. Okay, and remember this residual, this R is n-dimensional. It has a length n. Okay, it's a big long vector. So n-dimensional minimization problem, and we reduce that down to the right-hand side, which is only an m-dimensional least square problem. Okay, least square problem. Okay, so we are trying to minimize this right-hand side now. And this is equivalent to like solving this HM bar times Ym equals to beta Em. Okay, remember that this has HM bar has m plus 1 rows. Okay, so this is really a least square problem. It's over determined, so it's a least square problem. And then in MATLAB, you can simply just do a backslash HM bar backslash beta E1 and to get your Ym. And then, okay, then put the things all together. Our our approximate solution XM now is simply Vm times Ym. Okay. So this is quite GMRes is it's quite a straightforward. So means that at the end of your Arnoldi decomposition, all you need to do is just add these two lines of code. Okay, one line is to compute ym, and the other one is to compute your approximate solution. Add these two lines at the end of your unordinary method, then you have a GMRS for solving linear system. Okay. So this is great. Okay, so this is the idea behind GMRS. So now we can't wait to have a look at some examples. Okay, so example time. All right, so first example. So this is me just generate a matrix, a sparse matrix A, 20 by 20, with some density 0.3, and then some random right-hand side vector B. Okay, so for now, let's say we take 6 iteration. M is that's the Krylov subspace size. M is 6. Okay, and for now, we're gonna just use MATLAB's built-in GMRS function, okay, to implement this method. Okay, so on the left, this is the you've seen this type of plot from Tim's lecture. So on the left, this is you remember that Arnoldi method is really good at capturing eigenvalues. It's trying to minimize PMAB and minimize the norm of this PMAB, and then be careful that this PM here is different from the PM that we are talking about for GMRS. The PM for Arnoldi method. Let me write this down for you. Okay. This PM over here is really exactly. This PMA is this characteristic polynomial. Okay. And we see that this is the contour plot. Okay, contour plot of the magnitude of this PM Z, this polynomial. And we see that it's really good at capturing a few eigenvalues. It's certainly here, this biggest one has been captured, and a few, one over here, and maybe a couple here. Okay. So that's why we think, okay, it's great, right? And then on the right-hand side, they see the plotting the relative residual. Okay, the relative residual for our linear system, for solving our linear system. And then we see that for M is the 6, so it's roughly like here. Okay, for M is 6 and not much happening. Okay, the relative residual is still pretty up high, and it's even I keep increasing. So actually I did increase my the size of my Krylov subspace, keep going, and still not much happening until much later. Okay, until much later, maybe M is 19. Okay, the relative residual finally coming down. Okay, of course, when I take M is 20, yeah, you are solving the exact problem. Okay, you get the exact solution. Okay, that's no surprise. But what's going on here? Okay, so what do we see from this example? Okay, first impression, well, okay, this is, as I said here, this is discouraging. Okay, so we see that GMRS behave more like a direct method. Okay, it seems no use at all until it finishes by reaching M equals to N. So of course, at that point, it's iterative method, and it found the exact solution. For this example, N is only 20. Of course, you can do that, but if your N, your problem is huge, like N is a million or something, then certainly you can't do that, right? You can't afford to do that. All right, so now let's take a moment. Let's take a breath, okay? Let's ask ourselves, should we really expect we can do we can do better than taking m equals to n. Maybe this whole idea of projection method for linear system just not that great. Possible? Oh well, but before we throw it all away, let's analyze what's happening and see if we can learn something. Okay. All right. So this come to our convergence analysis. So the question on our mind are things like, okay, how quickly does GMRS converge? Okay. In the previous example, it doesn't come down until the very end. Okay, how quick it should converge? Okay. And how many iterations m must be taken before the relative residual reduced to a satisfactory level, like 10 to minus 3 or 10 to minus 6. Okay. And what properties of A determine the size of your determine the size of the norm of the residue, and so determine the convergence, the rate of convergence. Okay. So these are the questions on our mind. Okay, so now let's do some analysis. Remember that at the beginning, we say that our GMRS produce a solution at each iteration. Okay, at each iteration that which is a polynomial of A times B. And this can be written as, remember, right, this as Vm times Ym. Okay. And this residual vector is Rm equals to B minus AXM, and then replace xm with this polynomial times of A times B in here. And then the next bit is that we take B outside. So inside brackets, we have I minus A Q m minus 1 of A. So let's call this bit, and this is another polynomial. Let's call this one PM2. Okay, PM2. So this is a new one. And yeah, this PM2 is really 1 minus Z Qm minus 1Z. So this is the polynomial of degree m. And this time it has a constant coefficient. Okay, constant coefficient 1. Okay, so that means we have PM cubed 0 is 1. Okay, keep this in mind. This is quite important for GMRS. Okay, this is our GMRS property of our GMRS polynomial PM cubed. Okay. So now with this result here, and then we take norm on both sides. So the norm is really the residual norm is really the norm of this polynomial times B. So you see that again, we are solving the problem of minimizing the norm of a polynomial times B. Okay, but this time it's over a different space of polynomials. Okay, so this time our PM2 is this one. Okay, which has the constant coefficient 1. Okay, this is different from the Arnoldi method from last lecture. Okay, in the last one, PMZ, this is the characteristic polynomial of HM. Okay, and this one has leading coefficient 1. Okay, so the coefficient of Zm is 1. Okay, so 2 different polynomials. Okay, let's see how the next part. So this is our the norm of our residual. Okay, we just copy this line down here. So let's focus on GMRS. Okay, so to minimize this residual, we're really minimizing the norm of this PM2 times B. And this is the norm of this is definitely less than the norm of the product. Okay, the PMA times the norms of B. Or you can divide this norm of B to the left-hand side. So this is become the relative residual. The relative residual must be less than or equal to the norm of PM2A. Okay, since GMRS minimize the left-hand side, so we can write down this inequality. Okay, so basically we're saying trying to say that we are finding a polynomial PM2 over this space, over the space of degree n polynomial with constant coefficient 1. We're searching for PM2 in that polynomial space such that the norm of this PM2 is minimized, okay, smallest one. And this inequality determine the rates, the convergence rates of GMRS. So if you can find PM2 that the norm can keep the norm small, then that's great. That means you can converge fast. If you can't find a PM to keep the norm small, then by luck, then the convergence will be bad. All right, so the next question is that, yeah, so with this result, now our question is that for a given matrix A and a subspace size M, how small can this norm be? Okay, how small can this norm be? So now let's suppose our matrix A is diagonalizable. So that means we can write A as X diag lambda I X inverse. So PM2A, this is simply just equals to X diag on the, we just apply this PM polynomial on the diagonal values. Okay. So X and then times X inverse. Okay, so on the, you can imagine that on the diagonal, this part, okay? So this is, you have all the PM2 lambda 1, okay, and then PM2 lambda 2, okay? Let's pull this part. And then again, we take norms on both sides. So the norm of PM2A is the norm of this whole thing. And then this is definitely less than or equal to the product of each individual norms, okay? And then we also know the norm, the norm of X times the norm of X inverse is the condition number for X. Okay. And for the middle part, this part, so you think this is a diagonal matrix, right? And it doesn't matter you take one norm or infinity norm, it's gonna picking out the maximum, okay, the maximum value of this PM2, okay, over the spectrum of A. Okay, so this is for lambda I is the eigenvalue the eigenvalues for matrix A. Okay. So you're gonna picking out the biggest polynomial over the spectrum of A. Okay, so now we can combine this result. This is the norm of PMA. Okay, we can combine this and this result together to get to here. We combine the result together. We get the following theorem on the convergence of GMRS. Okay, where this PM2 is a polynomial of degree m with constant coefficient. This is quite important to keep this in mind. Okay, this is the constraint for our, the property of our polynomial. Okay. So what this theorem? Let's just quickly summarize what this theorem can tell us. Okay. So we are saying that if the condition number X is not too large, okay, and if the polynomial of degree m, PMZ can be found, and whose magnitude, whose magnitude on the spectrum of A decrease quickly with m increase. Okay, if that's the case, then our GMRS will converge quickly. Okay, so that's what we learned, okay, from this theorem. So in the end, it really depends on the property of our matrix, matrix A. Okay. All right. So now let's have a look. Some more examples. So yeah, before the first example was the eigenvalues are complex numbers. So so this one, let's pick a example that all the eigenvalues are real ones. Okay, so this is me again building a 20 by 20 matrix, and with real eigenvalues. So there are 20 of them, and because so I made on purpose that I have some small eigenvalues on either side of the origin. Okay, I did that on purpose. And we just pick some random right-hand side vector and then ran GMRS for different choices of M. Okay, okay, so that again, this figure, look, this is me plotting the relative residue against M. That's the size of our Krylov subspace. So again, it's not much happening, okay? So especially for this small m, okay, m is 6, it's 8, 10, not much happening, okay? The relative residue still quite high, and till very end, okay, when m is maybe 19, or of course 20 is converged, is solving the exact, getting the exact solution. All right, let's take a moment to think about what's happening here. So let's have a look at this one. Okay, this figure on the left here. So here we are plotting the polynomial PM. Okay, that's the thing, the norm of this. We are trying the magnitude of this PM. We're trying to minimize. If we can keep the maximum of this polynomial small, then that means that, okay, from our theorem before, then that means we can converge quickly. Okay, so let me take m equals to 14 because okay, not much happening. Okay, for small m. Okay, so now I'm just taking m equals to 14 to plot this PM, our polynomial, GMRS polynomial at rows eigenvalues. Okay, red dots are the real eigenvalues for the matrix A. And you see that for m is equals to 14, I'm having trouble to bring the maximum PM. Keep it small. I'm having trouble. Okay, still stay at like 1.2 something. Okay. And too much later, when I'm taking m equals to 19, okay, it's quite epic looking polynomial, up and down a lot, but it's finally is being able to bring this PM, the maximum of PM, down to 0.11. Okay, so what's the maybe it's a bit hard to see here. Let me make this a little bit bigger. So this here, the point I'm trying to make is that look at these small eigenvalues. Okay, remember I pick these small eigenvalues, okay, on either side of origin. Okay, so with m equals to 14, remember we also have another constraint, which is the PM cubed at 0 need to be 1. Okay, so I have another, so with m equals to 14, okay, it's really, it really, because the goal is that to keep this PM small, right? So it's with m equals to 14, it's really struggle to keep PM at these two eigenvalues small. Okay, until is, let's have a look at this one on the right hand side. Okay, until m equals to 19, finally, this polynomial is able to keep PM small at those two eigenvalue, and then quickly going up to up here to meet my condition PM at 0 has to be 1, and then quickly coming down again. You see that's the bit that m equals to 14, it just doesn't have enough number of the degree of freedom to be able to do that. Okay, that's why it's struggled. Okay, so it can't keep the maximum PM down to some value, some small value, until much later when m equals to 19 is with this epic looking polynomial is being able to, with some small m, some small eigenvalue, some small PM value here, and then quickly go up to 1, and then quickly come back down, okay, to be able to do this, okay, for finally at m equals to 19, and also keep the, keep the other, other PM values small as well, finally, okay. So that's the story here. So small eigenvalues, especially they are on either side of the origin. Okay, that means it's just the problem is not easy to solve. Okay, our PM will struggle to find a PM polynomial that being able to do this. Okay, from something small and quickly go up and then quickly come back down. Okay, it's really struggle to do that. So it's a hard problem to solve. Okay. So that's what we learned from this example. This is the example about small eigenvalues, right? So now let's move on. So now I'm thinking, what if, so I'm taking the matrix from example 2, and all I did is just shift my matrix becomes A plus I, okay? So I'm gonna solve this problem instead of solving the original problem AX equals to B, and then see what happened, okay? All right. So you see, okay, so you see again, okay, blue curve is my original problem that AX equals to B, and this time, okay, my red curve on the convergence, this is a bit better. It looks a bit better than the original problem. Oh, okay, let's see what's going on this time. So again, I'm plotting the polynomial, my PM2, over here for m equals to 6. Okay, for m equals to 6, that's roughly about here. Okay, for PM equals to 6, for m equals to 6, you can see that this is me satisfying my condition. PM0 has to be 1. So my polynomial quite comfortable that start from there and then comfortable get down and then trying to keep all the PM at lambda small, okay, that m equals to 6, and then move down to here at m equals to 14. Okay, it's doing a great job. Okay, start from 1 up here and very comfortable just going down, and then keep all the other polynomial values at lambda I also small. And at m equals to 19, yeah, it's great. It's basically, it's 0, it's very small. The maximum of PM at lambda is very small. Okay, so what we learned from here. Okay, so all we did, so we learned that for a problem like this, if I have a matrix like this one, then that means all my eigenvalues are positive. Okay, are all positive. I don't have those small eigenvalues hanging around on either side of the origin. And then make my polynomial can do a much easier, can do an easier job to just comfortably rolling down, and then try to satisfy keep other polynomial values also small. Okay, it's quite comfortable to do that. That's why we have a faster, we can see a faster convergence over here compared to the original problem. Okay. Okay, so the conclusion here is that we don't like small eigenvalues. Okay, if the eigenvalues can be away from origin, that's good. Especially if we don't like if they are on either side of the origin, that's bad. So now look at another example here. So this time I I build another matrix. Okay, still 20 by 20, and with eigenvalues clustered. You can see it down here with eigenvalue clustered around 5, 10, 15, 20. Okay, and then this yellow curve, the blue one is my original problem. The red one is a plus I, just shift a to the right. And then this yellow one is my clustered A. Okay, so we're solving this cluster problem here. All right, so it's this time you see that, wow, with m equals to 4, okay? With m equals to 4, I'm able to bring the maximum PM down to 0.04 something. Okay, so you see that it's quite comfortable to start with PM 0 at 1, and then rolling down, okay, capturing a few here, and then bring all the values down near to 0, okay? So the good thing that is that if one of them, one of the eigenvalues, if one of the polynomial values at the eigenvalues is small, that means that because they are clustered, so a few of them nearby, that means those polynomial values are also small. So that's the advantage of if you have clustered eigenvalues. So m equals to 4 is the maximum PM is pretty small, and then m equals to 6. Okay, it's improved again. So PM is 0.007 something, and when m equals to 8, it's already 0.00006 something. Okay, basically reach 0. That's why we see for a matrix like this, with eigenvalues clustered, okay, then you will get a faster convergence. Okay. Okay, now let's revisit our example 1. Okay, remember our example 1, I just randomly generate a matrix with some random right-hand side. So the eigenvalues come out complex numbers. And this is the blue curve is my original relative residual curve. Okay. You see not much happening until the very end. Okay, so now we can have a look what's the problem here. Okay, so now I'm plotting at m equals to 6. I'm plotting the contour, okay, because it's complex number. So this is the contour of the magnitude of PM tilde. Okay. So you see, apart from the capturing the largest, apart from capturing the largest eigenvalues, it's really struggle to keep the polynomial, the magnitude down to 0. Okay, remember here we still need to satisfy that condition. So here in the middle, there's in the origin, so it's roughly like here. Okay, so here there's a spike, right? There's a spike of your polynomial. So remember PM tilde. All right. PM tilde 0 has to be 1. Okay, so there's imagine if this is a 3D plot, then there's a spike, okay, coming out of the screen, and then there's 1, and then you need to quickly get down to keep the polynomial small at all the other eigenvalues. It's really struggle to do that. It's especially in you see these ones around the edges. That's really struggle to do that. Okay, so that's why this maximum PM is high. Okay, PM is high, and it stay like that, and it's stay like that for quite a while until the very end when M is like 19. Finally, it's being able to, you remember the plot for example 2, finally being able to quickly going up and then quickly going down. Okay, it's finally have the enough degree of freedom to do that. Okay, that's our original problem, example 1. And then on the right hand side, this is me again. I'm shifting my matrix. To the right. So I have my new matrix is really A plus 2I. Okay, My new matrix is really A plus 2i. And we are solving this again using GMRes with m equals to 6. So what we have this time, you see that my maximum PM is already pretty small. It's 0.03 something. Okay, so what we have on this plot over here is that my eigenvalues, you see my eigenvalues, I don't have, all my eigenvalues are on the right half plane. I don't have anything on the left half plane, not like this original problem. Okay, and that means I still have to meet my my constraint PM 0 is 1. So imagine here is a big spike, okay, coming out of the spring. Okay, a big spike at 1, but it's quite comfortable. All I need to do is just rolling downhill. Okay, rolling downhill to the right, and then to make all these PM to at lambda equals to some small, keep them at some small number. So blue means small. Okay, blue means the value is small. Okay, so you see that he's doing a great job at doing that. That's why the maximum PM tude is 0.03. It's quite small. So that's why we see this red curve down here. So for my shifted problem, I can achieve a much faster rate of convergence. Okay. Okay, so that's GMRes. All right, so now let's summarize what we learned here. Okay. So in GMRes, we have this linear system, AX equals to B, and the rate of convergence, depends on the condition number of the eigenvector matrix, like condition number of X, and how quick the magnitude of my PM at lambda I goes down with M. Okay, with this, remember this constraint PM tude at 0 is 1. This is playing an important role for the GMRes. Okay. And another thing we noticed that is, yeah, we don't like small eigenvalues. Okay, they are not desirable, and we like clusterings. Okay, in the example 3. Okay, so it's our, so how do I say? So the convergence is really problem specific. It really depends on what our matrix A look like. Okay, and then you say you think, okay, then all these properties are good to know, but if for my problem A, I want to solve my AX equals B, I can't just shift my A with I or 2I. I can't just change my problem. Well, that's true, but that type of thinking, okay, that thinking is great. That's actually will lead us to our next topic. Okay, I mean tomorrow. Okay, so tomorrow we will talk about preconditioning. Okay, so which can achieve a similar effect. It's changing the spectrum, the distribution of our eigenvalues. Okay, so that's tomorrow's topic. Okay, I feel, how do I do with time? It's 11:50.
Yeah, it's 11:50. So
I still
well,
have a few. Maybe I should cover this tomorrow. I still have a few more slides. What do you think? An idea?
yeah, okay, so we can move to questions, because I mean we still need to answer the questions. So
Okay.
probably there are some. So and then so the rest is tomorrow, right?
Okay, yeah, I can do that. Yeah, happy to do that. Yeah.
Okay, so for the questions, you can either put the questions in the chat or just unmute yourself and ask the question. So I don't think we will need a big queue here. So, and I will probably ask a question as usual, the first question from me, just to warm up the audience. So I was wondering if you use, say, some standard software, like for example, MATLAB. So
Yeah.
would this software already have, say, GMRest, for example, implemented when you try to solve linear system, or not really, and you have to actually somehow do it yourself?
It is. MATLAB has this GMRest function already. So let's come back to our first example. Yeah.
So in
Great.
MATLAB, it will be already implemented. So no need to do it for us.
If you copy this bit in MATLAB, it will, MATLAB already can implement this. It has
Sorry,
lots of other properties in there. You know, you can next week, not next week. I mean, tomorrow we can cover preconditioning. Yeah.
Sorry, but no, what I meant is that if you just simply, because you can just solve systems in MATLAB. So by default, they don't include GMRes. You have to explicitly write it in the command, right? So, I mean, when you just try to solve a linear system in MATLAB, so if you don't specify GMRes, then they will not use it, right? So
that's
okay, yes.
That's right. Yeah. So if we want to solve with GMRes, then we need to call this function.
Okay.
Yeah, sorry, I misunderstood.
No, just really because most of us would just solve linear systems without thinking, and then okay, so if you want something a little bit more advanced, so there is an option. It's just not the default one. Okay.
Hello.
Oh, hello.
Thank you for the lecture. I had a question about so when you want to approximate your solution at in the Krylov subspace of dimension m, you have to solve a problem. You have to solve the linear system with h m bar as a matrix. But this matrix completely changes at every iteration. So, like, do you need to resolve this system at every iteration for m, or can you like use the previous solution xm-1 to compute very fast the xm solution?
You need, because this HM is super small, usually, so it's very efficient to solve at each time, at next iteration. Yeah.
Okay, thank you.
Thank you, Ken. A question for both you and Tim. Are you going to cover in these lectures using sort of these Krylov subspace methods for computing other functions of the matrix? I have a particular interest in computing the square root of a matrix times a vector, because if you're given a covariance matrix and you want to generate a random vector with that particular covariance, then a simple way is to take a uncorrelated random vector and multiply it by the square root of the matrix. But of course, you're not given the square root of the matrix, and it can be very big. So I was just wondering, yes, are you going to cover those sorts of things?
Yeah, Gary, you got yourself a deal. I'll do it on Friday. How's that sound?
Okay. And just in connection with that, the matrices you've referred to for, where these things will work well, you've chosen sparse matrices as the, obvious candidate of matrices which are suitable for these methods. But I was just wondering if you'd done any work with H matrices or dense matrices but are still efficient to work with, in the sense that matrix vector computation is order n and as opposed to order n squared.
So so for now,
We're each waiting for the other to answer.
So for now, I think we focus on it. Suppose A is the sparse matrix. And but actually next week, not next week, sorry, I keep saying next week. I mean next lecture. So we will cover a little bit. Suppose that you for large problems, if you can't afford to have your VM is really a dense matrix. Every column is filling up with numbers. So if you can't afford to have a large VM, then what can you do, right? That's called a restarted GMRes. We're going to cover a little bit that, try to tackle problems like you just asked, I think. So we may cover tomorrow, talk a little bit more tomorrow on that.
Thanks very much.
Hi, thanks for your talk today. It was really interesting. I was going to ask a question about why the condition for PM0 was 1, but you scrolled to the slide, so I'm all good.
Yes. This time, because for the GMRes PM is different polynomial compared to Arnoldi PM. That's really a key difference. The two problems so different.
Yeah, I was going to ask if it was always a condition, but I think I was a bit late to the talk, so thank you.
No problem. Okay. So tomorrow we will cover restarted GMRes. That's a different aspect to implement GMRes, and also cover preconditioning. See if we can improve the spectrum distribution. So this week the examples are a little bit like cheating. I'm just making up a new matrix, a plus 2i or a plus I, try to improve my the look of my eigenvalues. And next week we're going to do it, not next week, I mean tomorrow we can do it properly with preconditional.
Okay, so the chat I think is empty. So if no questions, then we can finish for today. So thank you very much, Jan. And so if you want to share the slides, then please email them to me. I will upload on our website just how we were doing with Tim before.
Yep.
Okay.
I will do that. Okay, thanks everyone. Nice to see everyone. I see you tomorrow.
Thank you.
Yeah.
Okay,
Bye
for now.